All right, so what we're going to look at today is an introduction to antidifferentiation. So if we just get straight into it and think about two functions, if you've got this pink function here, which is the derivative, is equal to 2x, we could say to ourselves, all right, then the original function must have been x squared plus something, right? Because if we shift that blue function up or down, it doesn't change the value of the gradient at any of those x values. So you can see how we're shifting this up or down. It doesn't affect the derivative of that function because, for example, at x equals 0, if you shift it up or down, that doesn't change where the derivative goes to 0. It goes to the derivative. You get a horizontal tangent line at x equals 0, no matter how much you shift it up or down. So you can see why the gradient graph, g dash of x, is always equal to 2x, no matter how much you shift g of x up or down. So to start thinking about this idea of antidifferentiation, well, just think about the opposite of differentiation, right? So you're going from, some function, you're trying to find what was the original function such that the derivative, in this case, is 2x. So we can say that the antiderivative of 2x is x squared plus something we're not sure. It could be some real number that we've shifted it up or down. So if we put some notation onto that, it might look something like this. So this is the notation we use. So the general antiderivative of 2x is x squared plus c, where c is an arbitrary real number, because as we said, we can shift it up or down. And the notation we use is this. So we would read this as the integral of we would say the indefinite integral of 2x dx is equal to x squared plus c. And, if we sort of summarize that, we say that if capital F dash of x is equal to f of x, okay, then the integral of f of x dx is equal to capital F of x plus c, where c is an arbitrary real number. Okay, so basically it's saying if you integrate some function f of x, it'll give you an antiderivative of that function. And you have to include this constant of integration, which we call c. All right. If we think about some general rules now of antidifferentiation, we're just going to talk about the rules, and you could study these and think about why they're the case until the cows come home. But this is the sort of screen you might want to sort of screenshot, because this is what will be given on formula sheets and things. So these are a bunch of different rules that tell you how to find the antiderivative of a function. So if f of x, for example, is equal to x to the n, then the antiderivative of that is equal to x to the n plus 1 over n plus 1 plus c. I'm not going to go through all of them, but that's the sort of prerequisite knowledge we're going to need in order to understand more challenging integration techniques that we'll come across soon. Okay, to sort of maybe talk about one other important thing, we can talk about what's called the definite integral. You might have noticed before I mentioned the indefinite integral, where we've got this constant of integration. What we can talk about now is what's called the definite integral. So if you take an integral, so an antiderivative essentially between two values a and b, that is what's called the definite integral, and it denotes the signed area enclosed by the graph of y equals f of x, the x-axis, and the lines x equals a and x equals b. So it'll make sense in a moment, but what we would do is write it like this. The integral from a to b of f of x dx is equal to capital F of b minus f of a, where those capital F's, remember, represent an antiderivative of the original function. So we'll show you a picture here in a second, and let's just be careful here as well. So the a represents what's called the lower limit of integration, and b is the upper limit of integration. And the function f is called the integrand. So yeah, I'll put some links below for the fundamental theorem of calculus explaining what on earth antidifferentiation has to do with area. But just to sort of tie this together, you can see in this function here, we've just got in blue the function y equals x squared. And the left-hand edge of that pink shape, is the lower bound of integration, which we call a, and the right-hand edge is b. And so what we're saying is if we take an antiderivative of f of x and we find what that is, that's going to be capital F of x. But if we substitute in the upper bound f of b and subtract f of a, that tells you how much area there is underneath the function, which I think is fascinating. And it's not at all obvious why that's the case, but as I said, the fundamental theorem of calculus ties that all together. So I'll put a link below. Definitely go and watch that because it's absolutely fascinating, I think. So that is how you take a definite integral. And you notice here there's no constant of integration, there's no plus c, because we're finding an area. And I'll just point out as well, we're finding what's called a signed area, because areas above the x-axis are considered positive, areas below the x-axis are considered negative. So when we say the signed area, we're saying, because you could imagine a function where you've got some area above the x-axis and some below, they're going to cancel each other out to the extent that there's a positive amount equal to a negative amount. The positive, if for example the area above the function was equal to the area below the area above the x-axis is equal to the area below the x-axis, think of like a sine graph, then the signed area would be 0 because the part above would cancel out with the part below. So yeah, we just need to be careful that we're finding what's called the signed area. It's taking into account the signs of the area. Okay, hopefully you found that useful. If you did, give us a thumbs up. It's a very brief introduction to anti-differentiation. We'll talk more about it over the coming lectures. Like and subscribe if you haven't already, and we'll keep this going. We're almost halfway through the specialist course, and get in touch if you've got any questions, and I'll talk to you soon.